So we're going to shake a cocktail, and the question is, what temperature will that cocktail get when I shake it? But before we start, let's take a look at the case of ice and water. So I have a stirring glass here with a thermocouple in the bottom. I'm going to take some ice water, and I'm going to stir it. Right now the temperature is about 1 degree Celsius. I'm going to stir it because I got to chill the probe in the glass down to the temperature of the water. And you can see that within the accuracy of my thermocouple, right now it's reading about 0.4, 0.3 degrees Celsius, that's where it is. And no matter how long I stirred, if I sat here and stirred all day, 0.2, it would stay this temperature until all the ice had melted and the temperature started going back up towards room temperature. So clearly when you're stirring just ice and water, it stays at 0 degrees Celsius.
So there's a specific heat that ice has, and so if you plot heat as a function of temperature with a slope basically dependent on the specific heat up until you get to the freezing point of water, at that point it's going to change phase, and the specific heat of water is actually different than that of the specific heat of ice, and so the slope will actually change. However, there's one other thing that you need to know, is that if you're continuing to add heat, when you get to 0 degrees, there's this plateau region where you have to keep giving the thing heat and the temperature doesn't go up at all. It stays at 0 degrees until you've put in a certain amount of heat, at which point the solid ice becomes a liquid, and then the temperature starts to go up again when you add more heat. So that extra heat that you have to add to cause the solid to become a liquid is called the latent heat of fusion. It's the extra heat that you have to put in to essentially change the molecular structure, the material of that from a solid to a liquid, to allow it to continue to jiggle around more as it heats up. But when you get to 100 degrees, we know when you add more heat, what should happen is that the liquid water should change to a gas. But it turns out that, again, there's some amount of heat that you have to add in order for that to occur. That heat, the heat that you have to add to cause liquid water to change to a gas, is called the latent heat of evaporation. So the latent heat of fusion for water, it turns out, is 335 joules per gram. The latent heat of evaporation is 2,260 joules per gram. And these numbers actually, it turns out, for water are really rather large and are one of the reasons for the sort of peculiar ability of water both as a cooling agent and as a heating agent.
And what you'll see when I shake this cocktail is that quite rapidly the temperature is going to shoot down and then go well below 0. And if I shake it really well, I can get it anywhere between -5 up to -8 sometimes degrees Celsius.
And so let's just, for the sake of argument, imagine that in our cup we have 10 grams of ice. So I told you that the latent heat of fusion is 334 joules per gram. So if I want to melt 10 grams of ice, which is the ice that I'm putting into my glass of water, then that requires 10 grams times 334 joules per gram, and that's 3,340 joules. So that's actually how much energy is required. And so that's the amount of energy that is going to be taken out of the water that I have in the first place, or whatever the beverage is that I have in the first place, that will cause the temperature to lower. How much will it cause the temperature to lower? Well, let's just assume, for the sake of argument, we have about 800 grams of water. That's a sort of typical amount of water. If we then take 800 grams times Cp, which is the specific heat of water, times delta T, and we set that equal to 3,340 joules, then what we find is that the temperature of 800 grams of water has dropped by about 1 degree Celsius. If I'd used 100 grams of ice, then it would have dropped it by about 10 degrees Celsius. That's starting to get significant. And this starts to explain to you why, if you just dump a lot of ice in your water, it really can cool it. The cooling power is really quite enormous.
Cheers. Not bad.